In this video, we're going to talk about the Chinese remainder theorem. Before watching this video, you should have an understanding of modular arithmetic, including how to find a modular inverse. Suppose we have x is congruent to 2 mod 3, x is congruent to 3 mod 4, and x is congruent to 1 mod 5. We wish to find a solution x that will satisfy all three congruences. The Chinese remainder theorem is a rather involved algorithm, and I find it helpful to label as much as possible in order to make obtaining the solution easier. Our first step is to take a look at the greatest common divisor of all three of our mods. This greatest common divisor, or GCD, must be equal to 1 in order to use the Chinese remainder theorem. So the GCD of 3, 4, and 5 is equal to 1. Therefore, we know that there's a unique solution, mod 60, where 60 is obtained by taking the product of 3, 4, and 5. So our goal is to solve an equation of the form A3, M3, Y3, in other words, the product of A3, M3, and Y3, plus A4, M4 times Y4, plus the product of A5 times M5 times Y5. And we wish to say that this is congruent to some number mod 60, where this number represents our solution. Let's identify our values of A, M, and Y. To begin, we denote uppercase M as 60, the product of our three mods. Therefore, M sub 3, which corresponds to mod 3, is equal to 60 divided by 3, which is equal to 20. M sub 4 is equal to 60 divided by 4, which is 15. And M sub 5 is equal to 60 divided by 5, which is 12. Next, let's determine our values of A. A sub 3 is equal to 2, because that's the remainder for mod 3. A sub 4 is equal to 3, and A sub 5 is equal to 1. Now finding our y's presents a bit more of a challenge, so we'll work that out on the next screen and then come back to this one. Recall that m sub 3 is equal to 20. If we wish to find y sub 3, we begin by saying y sub 3 is congruent to the modular inverse of 20 for mod 3. There are a couple of ways to find inverses. We're going to use the naive method, which is sort of a trial and error method. For mod 3, we know that we can have remainders 0, 1, and 2. So, beginning with remainder 0, we take 20 times 0. This is congruent to 0 mod 3. Then we take 20 times our next remainder, 1, and find that this is congruent to 2 mod 3. Next, we take 20 times the remainder 2, and find that this becomes equal to 1 mod 3. Since 2 leaves us with a remainder of 1, we know that y sub 3 is equal to 2. Next, we wish to determine the modular inverse for y sub 4 congruent to modular inverse of 15 mod 4. We're going to use the same process, only this time possible remainders are 0 through 3, since we're working in mod 4. I begin the same way as I did for the last problem, using the naive method. So first I take 15 times 0, and I find that that is congruent to 0 mod 4. Next, I take 15 times the remainder 1, and I find that this is congruent to 3 mod 4. In the next step, I take 15 times 2, and find that this is congruent to 2 mod 4. And finally, I take 15 times 3, and determine that this is congruent to 1 mod 4. And that's what we were looking for, is our remainder of 1. Since we have a remainder of 1, when we use the remainder of 3, we find that our modular inverse is 3. In other words, y sub 4 equals 3. Finally, we find the modular inverse for y sub 5. We set y sub 5 congruent to 12 inverse mod 5. And since we're in mod 5, possible remainders are 0 through 4. So we take a look. 12 times 0 is congruent to 0 mod 5. 12 times 1 is congruent to 2 mod 5. 12 times 2 is congruent to 4 mod 5. and 12 times 3 is congruent to 1 mod 5. So since we have found 1 mod 5, we can stop here, and we know that y sub 5 is equal to 3. I've now learned that y sub 3 is equal to 2, y sub 4 is equal to 3, and y sub 5 is equal to 3. Revisiting our formula, now that I have all of my values for a, m, and y, I'll be able to find the unique solution mod 60. Again, we wish to solve a sub 3, m sub 3, y sub 3, plus a sub 4, m sub 4, y sub 4, plus a sub 5, mod sub 5, m sub 5, y sub 5, congruent to some number mod 60. Substituting all of our known values for a, m, and y, we have 2 times 20 times 2 plus 3 times 15 times 3 plus 1 times 12 times 3, all congruent to some number mod 60. Taking the product of each group and summing the products gives us 251 is congruent to some number mod 60. And ultimately, 251 is congruent to 11 mod 60. This concludes our example. The solution we have found is x equals 11. This value of x will satisfy each of our congruences. Anyway, this concludes our example, and we'll see you next time.